busy.
Okay, I'm going to close this question in 5, 4, 3, 2, and 1. All right. And here are our responses. Okay. So these are the most popular answers. So converting methane liquid to methane gas is a physical process. Yeah, thanks so much. Okay. And solid CO2 to gaseous CO2 physical, and solid water to liquid water, just like in rain, okay, is physical. But something like photosynthesis, converting carbon dioxide in H2O into glucose and oxygen, is a chemical process. And burning like CH4 into CO2 and H2O is a chemical process. Now, what's the main difference you see here between a physical process and a chemical process? If you're given a question like this in an exam or a quiz, okay, what are we looking for here? What's the main difference? Anybody? Ethan, thank you. Thank you. The change in the substance, right? You can see that in a chemical process, you are changing the composition of the substance. In photosynthesis, we started with CO2 and H2O and ended up with oxygen and glucose, which are totally different from what we started with. Okay. When we are burning propane, we are converting propane into carbon dioxide and H2O, which is completely different from what we started with. Okay, so that's the main feature of a chemical reaction, okay, that we use to identify or distinguish that from a physical process. Okay, and what is that again? We are changing the identity of the substance. We are changing the chemical composition of the substance. All right. And that's feature 1. So feature 1 goes like this. In the chemical process, okay, we are starting with initial substances called, anybody? The initial substance of a chemical reaction is called, what do we start with in a chemical reaction? Thank you, reactants. And then we end up with final substances called products. Thank you, which are chemically different. Okay, composition was that different. Okay, and that's the feature 1 of a chemical process. And that's the main one. Okay, that's the main one you're going to be using to identify a chemical process out of, a bunch of processes like physical processes. Okay, we start with reactants and end up with products, which have a different chemical composition. That's the main thing. And apart from that, there are some other features of a chemical process, okay? And usually there's going to be a net energy transfer, meaning some reactions release energy to the environment. We call them exothermic process. And some reactions absorbs energy from the surrounding, and those are called endothermic processes, okay? And then the next feature is the rate of the reaction. Some reactions are really, really fast, like an explosion. It occurs really instantaneously. Okay, but there are some other reactions that takes like forever. I mean, figuratively, right? For an example, like rusting. Okay, it's a process that takes a lot of time. And then some reactions go to completion, like 100% completion, but most of them don't. Okay, meaning at the end we have like products and reactants together. Okay, and we call that an equilibrium state. Okay, so these are the signature features of a chemical reaction. And then I have never seen a question asking you to, list the features of a chemical reaction, but we will be testing the understanding of, a difference between a physical and a chemical process. Sure. All right. Do we have any questions, concerns, comments at the moment? Anything? Okay. So if that is the case, let's try to understand. So what we want to do is, as scientists, we have something in our hand now. We have a chemical reaction, right? What we want to do is we want to explain it. Okay. So when the scientists are asked to explain something, what do they do? How do they explain things? Anybody? What do we do? We explain. Yes, sir. Thank you. Thank you. We come up with a model, which is based on a bunch of assumptions. All right. By the time we go through the assumptions, we can explain everything. Of that phenomenon. That's the idea there. Okay. So anyway, So we'll be using a model to explain the chemical reaction. And this model has assumptions too. And this has 6 assumptions. All we do in Unit 4, Module 1 is going over these 6 assumptions. And that's it. And we're done. Okay. Now, before I talk about the assumptions, before I start talking about the assumptions, I want you to make a note in your own words about the model. Okay. This model roughly goes like this. Okay. Please make sure that you have like a clear idea about this in your head, and make as much notes as possible, because this is very important. If you understand this simple model, you're going to do really well in this unit. Okay. And it goes like this. It's very simple. Okay. We have a box. Imagine a box. Okay. In this box, we have reactant molecules. And these reactant molecules are not going to stay still. They're going to move around constantly in random directions. Sounds familiar, right? And because of this random motion, they're going to collide with each other. Okay. When they collide, there'll be an energy transfer, and then the atoms are going to rearrange to produce new substances called products. That's it. That's the model. One more time. Okay. We have a box. Okay. In that box, we have reactant molecules. Imagine in the gas state. Okay. We have reactant molecules moving around in random directions. Okay. During their movement, they collide with each other. Okay. And these collisions lead to rearrangement of the atoms to make new substances called products. That's it. What does assumption 1 tells you? Anybody? I know everybody wants to talk, but anyway, I think I'm gonna talk to someone randomly. Liv, what do you think? What does it say? Assumption 1. Can I have the microphone with Liv? I know she wants to talk. Thank you, Liv, for volunteering.
It means the atoms that make up the reactants are rearranged
to form the new substances called products, and that's it.
Yep.
Yeah, that's basically it. Thank you. Okay. Now, anyway, in my mind, assumption 1 says, I can summarize assumption 1 to just, 2 words. Conservation of mass. That's it. Assumption 1 says, during a chemical reaction, the mass is conserved. Okay. What do I mean by this? What I mean by this is, during a chemical reaction, we cannot create or destroy atoms. Okay. Because, creating or destroying is, it's playing God. We're not going to play God. We're just chemists. Okay. We're just going to rearrange the atoms, but we are going to end up with the same atoms we started with. In the final step. That's it. All right. Do we have any questions, concerns, comments at the moment? Anything? Okay. So one more time. Assumption 1 says, during a chemical reaction, the mass is conserved. That's it. Okay. Now let's play with this. So we're going to start playing with this today. Okay. And also this actually, goes on to Unit 4, Module 2 as well. This is what we're going to be doing in Unit 4, Module 2 as well. All right. Here's an example. Let's take methane, CH4, and burn that in oxygen. Okay. We also call this a combustion reaction. Whenever we react something with oxygen, okay, it's an oxidation reaction, or an oxidation or combustion in this case. Okay. So if I go to my notebook for a second, okay, what we are doing here is, let me see if I can quickly go to a new page. We have CH4. Okay, we have CH4. We react that with oxygen. Okay, does somebody know what we get from this reaction when you burn CH4 in oxygen? What do we get? Yeah, I heard that. We get CO2. If it is a complete combustion, you're going to get CO2 and water. Yeah? And water. This is what we get, H2O. Okay. If you burn something that contains carbon and hydrogen, you will get carbon dioxide and H2O. But you don't have to be able to predict the products of a chemical reaction, by the way. but you just need to being able to, play with this, this chemical reaction. That's it. Now, here's the thing. Okay. Now you see that we have how many hydrogen atoms on the reactant side? Everybody, how many do we have on the reactant side? Hydrogens. 4. Thank you. On the product side, how many do we have? 2. So what have we done here? We have destroyed 2 hydrogen atoms. This is a no-go. We cannot do that. So what do we do now? How can we fix this? Annie? Okay, now how do we balance the hydrogens then? Thank you. We multiply the number of H2O by 2. Okay. Now, when we do that, we have 4 hydrogen atoms on the product side as well. Okay. Carbon, we have 1 on the reactant side, 1 on the product side. I'm not going to touch it. It's fine. It is balanced. Okay. Oxygen. How many do we have on the reactant side? Everybody, please. 2. Thank you. How many on the product side? Everybody. That was lame. I know it's okay. One more time. How many on the product side? 4. Thank you. We have 4. What have we done? We have played God here. We cannot do that. Okay. We need to make sure that we have the same number of atoms on the reactant side as well. So what do? We need to have 4 oxygen atoms on the reactant side as well. What can I do to do that? Thank you. We can multiply the number of oxygens by 2. There you go. Okay. Now, this is what is meant by balancing chemical reactions. Okay. And where this is stemming from? This is stemming from the first assumption of our model, or the conservation of mass. That's it. All right. What questions, concerns, comments do we have at the moment? Anything? Okay. I want to mention one other thing while I'm looking at this. These numbers in front of these species are called stoichiometric coefficients. Stoichiometric coefficients. Okay. So there's an implied 1 here. We don't have to write the ones. Okay. So there's 1, 2, 1, 2. Okay. These are called stoichiometric coefficients. Okay, they play an important role, with what we're going to be doing next with these equations. All right, do we have any questions, concerns, comments about this? Anything? Anything? Okay, so if that is the case, let's do this. I'm going to go back to my slideshow. Okay. Now, by the way, in a chemical reaction, we have the initial state. I like to call this initial state, not the reactants or products. This is my initial state. Okay. And this is my final state. Right. I'll come back to why I call them initial state and final state rather than reactants and products in a second. It will be obvious to you in a second. Okay. So let's think about, okay, it's the same thing. We just talked about this, balancing chemical equations and stoichiometric coefficients. Okay. Anyway, now let's think about this reaction now. Okay. What I want you to do is, on your whiteboards, I want you to write the balanced chemical equation for this process. Now, in our reactant side, we have H2S, okay, and oxygen. And then we are ending up with SO2 and H2O. That's what we're saying here. Right? Anyway, I'm going to close this question in 5, 4, 3, 2, and 1. So I just want to know how we did for the moment. Okay. All right. So these are our options. Okay. You're between A and B mainly, and then maybe some of us are in C as well. Let's see what's going on here. Okay. Now, here's what I would do. I'm going to switch to my notebook for a second. Okay. And again, I have H2S reacting with oxygen to produce SO2 and H2O. Okay. Now, again, let's do this together. Okay. If you do this with me once, okay, or maybe twice, okay, then I mean you should be very comfortable with doing something like this. All right, hydrogens. How many do we have on the reactant side? Everybody. That was lame. I didn't get the answer from everybody. How many hydrogens do we have on the reactant side? Better. Thank you. 2. How many on the product side? 2. So I'm not going to touch hydrogen. Why? Hydrogens are balanced. Okay. Sulfur. How many on the reactant side? How many on the product side? I'm not going to touch sulfur either because that is balanced. Oxygen. How many on the reactant side? How many on the product side? Oh, we have a problem there, right? So we have 3 on the product side, but we only have 2 on the reactant side. This is what I'm going to do. I'm going to multiply my oxygens on the reactant side by 3, but that would give me 6 oxygen atoms. Okay, but if I divide that by 2, then it's going to give me three oxygen atoms on the reactant side as well. Right now, I have a balanced chemical reaction, balanced chemical equation. Even though by convention, we do not like to keep fractions in our balanced chemical reaction. So what do? I multiply everything by the denominator, which is 2. If I do that, I'm going to get 2H2S and 3O2, 2SO2, and 2H2O. As my balanced chemical reaction. Done. And then I would look for this answer in my options. That's what I would do. All right. What questions, concerns, comments do we have at the moment? Anything? I mean, you might have other ways of balancing your chemical reactions. You know, you do you. If it works for you, it's totally fine. But this is how I do it. I just want to show you how I do it here. All right. Anyway, any questions, concerns, comments at the moment? Anything? Okay. So I'm going to reopen these questions, but I'm going to let you ask me questions before I, start talking about things. Let's clear my doodling. And here we go. Okay. So now, yeah, I have a question. Yes. What's your name, Miss?
Delia,
Delia, go ahead.
can you go back to the representation again?
You mean my notebook?
No, the question
Oh, yeah.
with like
Yes.
yeah. So in the products, there's the H2S's. What happens with those in the reaction?
Thank you. Okay. Now, Dalia's question is, we see that we in the final state, by the way, this is not products. This is my final state. This is my initial state. We have some leftover H2S. Okay. Yeah, it's true. I have that. But I do not write in my balanced chemical equation. I do not write, get this, products on the reactant side or reactants on the product side. Okay. Reactants have no business on the product side and vice versa. Okay. Products have no business on the reactant side. Therefore, no products on the reactant side or no reactants on the product. They said the same thing. Anyway, you got what I said, right? Anyway, so please keep that in mind. In the balanced chemical reactions, reactants are on the left-hand side always, and the products are on the right-hand side of the arrow, always. All right. Any other questions, concerns, comments? Okay. One other thing. Dahlia, did that answer your question, Dahlia? Did that answer your question? Okay. All right. One other thing, and that would be this answer over here, option C. Okay. Why is that incorrect? Okay. So anybody, why is option C incorrect? Annie? Yeah. So whenever you write the balanced chemical reaction, you need to write the simplest version of the reaction. Okay. So all of these numbers can be divided by 2. Okay. Therefore, the simplified version would be option A, right? That will bring us to option A. So that should be your correct answer. Okay. Any questions, concerns, comments about this? Anything? And there are 2 important points here. Okay. One more time, I'm going to summarize them. Okay. Number 1, you never write reactants on the product side or products on the reactant side in the balanced chemical equation. Okay, if you did that, please make a note now so that you won't do that again. Okay, you never write reactants on the product side or products on the reactant side of the balanced chemical equation. Okay, number two, you write the most simplified version of the reaction. Okay, simplest whole number ratio between the reactants and the products in the balanced chemical reaction. Okay, if it is not simplified, that is not the correct balanced chemical reaction. All right, any questions, concerns, comments at the moment? Anything? All right, if that is the case, let's do one other question. Okay, there you go. It looks much better. Some of us don't want to change it. Okay, anyway. All right, option B is incorrect. Okay, we talked about that. Let's see. All right, let's do this. Oh, by the way, before I move on, now according to this representation of submicroscopic representation, one of the reactants is limiting our reaction. Which one is it? Can you write the answer on your whiteboards, please? Which reactant is limiting the reaction? I want to see the answer on your whiteboards. What is the limiting reactant in this reaction? All right, can I see your whiteboards, please, everybody? I see. Okay, I see mainly oxygen. Okay, mainly oxygen, mainly. All right, so let's see why that is the case. Now, one more time, okay? In the final state, we see that we have left over H2S, meaning H2S is in excess. We have more of excess than we need. That's what this means. Okay? If we have that in excess, can it limit the reaction? No, it cannot limit the reaction because we have that in excess. Therefore, the other reactant, which is oxygen, must be our limiting reactant. Therefore, oxygen is our limiting reactant. Okay, this is the idea of limiting reagent or the limiting reactant. This is sometimes known as limiting reagent as well. Reactant or reagent. All right. Any questions, concerns, comments about this? Anything? Yes. Holly. No, I cannot do it. Yeah, you need more information to determine the limiting reactant. The chemical equation does not tell you the limiting reactant. Okay, so remember the balanced chemical equation is like the recipe. So if you're making, I don't know, a pumpkin pie, okay, you have the recipe, right? This like 500 grams of sugar and 2 grams of flour or something like that. Okay, but in actuality, you go to Fry's or somewhere and buy, I don't know, 300 grams of sugar and then 500 grams of flour. Okay, so that's how we can determine what is limiting. Based on that information, you know sugar is limiting because you need 500 grams of sugar according to the recipe, but you only bought 300 grams. That means sugar is limiting your reactant. Okay. So to do that, you need to actually go to the shop and buy the stuff, actually do the experiment. So the submicroscopic representations shows you what you have actually in a chemical reaction. Okay, you need that information to determine the limiting reactant. Kali, yeah. Okay. So with that, let's do one other thing. Right, here's another one. Okay. Determine the balanced chemical reaction and the limiting reactant. Go ahead. Right. One more time. Why is D incorrect? Why is D incorrect? The most popular wrong answer. Why is it incorrect? Thank you. We have the reactants on the product side, right? We have oxygen on the product side. This oxygen has no business being on the product side. Therefore, this reaction is wrong. Okay. I know that most of you who selected option D just counted the molecules on the product side and, wrote them here. So don't do that. Okay. It's a balanced chemical reaction. You don't need this. If you know the reactants and the products, okay, you can just balance the equation without even looking at it. All right. And then the limiting reactant. Can I see the answer for the limiting reactant on your whiteboards, please? The limiting reactant, I see CH4, mainly CH4. Okay, mainly. All right. Now, let's see why that is the case. Okay. I'm going to show you in a different way now. Okay. So we know, according to the balanced chemical reaction, to react with one CH4, we need two oxygen molecules. That's going to give us CO2 plus H2O, two of them. Okay. So react with one, we need two O2s. Okay. So here's one setup. Here's another setup. Now we have oxygen, but we ran out of CH4 already. Okay. Therefore, CH4 is limiting our reaction. Why? We ran out of CH4 first, meaning CH4 is limiting. Okay. Other way to determine this is we see that we have an excess oxygen, okay, molecule or leftover oxygen molecule on the in the final state. Okay, meaning oxygen is in excess, meaning it cannot be the limiting reactant. Therefore, the other guy has to be the limiting reactant. All right. What questions, concerns, comments do we have at the moment? Anything? All right. So that is that. Let's do this now. I hope I have the right one. Okay, here we go. This time, I'm not going to give you a sub-microscopic representation. Okay, I'm going to give you the moles or the molecules. Oh, here, this one is about moles. By the way, we are in Unit 4, Module 2 now. What? Yeah. Right. So before I look at your answers, I'm going to show you the way I think about this. Okay. And this is how it goes. Okay. According to the balanced chemical equation, this is what we have, 2 and 2 over here. So we will always start with that. Now we are told that we have excess oxygen. That means oxygen cannot be the limiting reactant. The limiting reactant must be CH4. Once we know the limiting reactant, get this, the limiting reactant calls the shots of the, governs everything about that reaction. Okay. So anyway, so we know CH4 is the limiting reactant. Okay. Because this is in excess. Now, according to the balanced chemical reaction, if we had 1 mole of CH4, how many moles of H2O do we get? With 1, we're going to get how many? Yeah, with 1, we are going to get 2. You know what? Let me write this here. CH4 and H2O. Okay. So with 1, we are going to get 2. How do we know that? That's from the stoichiometric coefficients. With 1, we are going to get 2. Okay. Therefore, with 10, how many will we get then? Yeah, we're going to get 20. Is that what they're asking? Is that what they're asking? I think that's all they're asking, right? Yeah. So therefore, we're going to. So here's the next step. Let's say that we have 25 moles of methane and 25 moles of oxygen. I'm giving you the moles of both reactants. Okay. If that is the case, how many moles of CO2 will this produce? Go ahead. Yeah. 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 So the chemical reaction is still the same, right? Whenever you burn CH4 in oxygen, you are going to get CO2 and H2O. That has not changed. Right? We even balanced it like that. All right. I think that should be enough time for discussion. Okay. I'm going to close this question in 5, 4, 3, 2, and 1. Okay. Now, before I look at your answers, I'm going to do this in my notebook, okay, so that everybody will be on the same page. All right. So there are two ways of handling this. Okay. There's one way where you need to think a bit, but you need to do little work. Okay. So there's the second way where you do not need to think that much, but you need to do more work. Which one do you prefer? Think more and less work, or do more and think little? Do more, think little. Okay. All right. How about this? How about I show you both methods? Okay. First I'll show you the thinking, and then, without thinking as well. Okay. So let's do it like this. Okay. Right, here's what we have. We always start with the balanced chemical reaction. Okay, so this is the balanced chemical reaction. And then, okay. So based on this, to react with 1 mole of CH4, how many moles of oxygen do we need? With 1, how many do we need? 2. With 1, we need 2. With 25, but you have 25 of this and 25 of oxygen, right? So with 25 moles of CH4, how many moles of oxygen do we need? Everybody, we need 50. We need twice as much as the number of methane, right? Okay, to react with 1, we need 2. To react with 25, we need 50. This is what we need. Okay, but guess what? How many do we have? We only have 25. We have less than what we need. If we have less than what we need, that means that reactant is limiting our reaction. Okay, so we just determined our limiting reactant to be oxygen. Is limiting. Okay, once we do that, okay, so once we do that, everything about this reaction will be governed by the limiting reactant. Okay, we don't even care about CH4 anymore. We only care about oxygen. Okay, now they are asking about how many moles of CO2 that you're going to get, right? So let's think about that. Okay, now between oxygen, which is the limiting reactant, and CO2, let's see the relationship. Okay, if we had 2 moles of oxygen, how many moles of carbon dioxide will we get? Everybody, if we had 2 moles of oxygen according to the balanced chemical reaction, how many moles of carbon dioxide will we get? Everybody, 1, right? With 2, we are going to get 1. Say that we had 1 mole of oxygen. How many moles of carbon dioxide will we get then? If we had 2, we get 1. If we had 1, we're going to get? Everybody. Thank you. 1/2. We just divide this number by this number. That's it. We're going to get 1/2. Okay. And now what we know that we have 25. So how do we determine how many we get for 25? We know how many we get for 1 mole of oxygen, and multiply that by 25, and that will tell you how many moles of carbon dioxide you will get with 25 moles of oxygen, which is going to be 12.5. That's it. Okay, that's how we can tackle this. Okay, first determine the limiting reactant, and then think about the relationship between the limiting reactant and what they're asking for, and then you just solve this. That's it. Okay, so other way to do this is, say that you did not do the limiting reactant first. Okay, you can do 2 calculations. Okay, one assuming the limiting reactant is CH4, the other one is assuming limiting reactant as oxygen. This is what I mean. Say that our limiting reactant was CH4. Okay, if that is the case, so if we had 1 CH4 mole, we're going to get 1 mole of carbon dioxide. With 1 CH4, we're going to get 1 based on the balanced chemical reaction, right? With 1 CH4, With 1, we are going to get 1. How do you know that? From the balanced chemical reaction. With 1, we're going to get 1. Okay. But we have 25. Therefore, we should get 25 moles of carbon dioxide if CH4 was the limiting reactant. Okay. On the other hand, if oxygen was the limiting reactant, okay, we know with 2, we are going to get 1. From here, 2, we are going to get 1. Okay. With 1, we are going to get 1/2. Therefore, with 25, we are going to get 1/2 multiplied by 25, which is 12.5. Okay. Between the two numbers, okay, this is calculation 1, calculation 2. Between the two numbers, we see that 12.5 is lower than 25. Okay. So whatever the calculation that produced the lower number is our limiting reactant. Okay. Therefore, the answer is 12.5. The lower number is the answer. That's the other way of doing it. That involves less thinking. Okay. You do 2 calculations. Whatever the calculation that produced the lower number is your answer. And that tells you the limiting reactant as well. Okay. You can do whatever, whatever works for you. Those are the 2 ways of doing it. Anyway, do we have any questions, concerns, comments about this? Anything? Any questions? Anything? Yeah? All right. Sydney, we're doing okay? Yeah? All right. Please, if you have any questions, don't hold them back. Okay. Chances are there are other people. Tessa, do we have any questions? Okay. Okay. All right. This is all you have to do. This is it. We're done. Okay. All right. Now, here's the thing though. When you go to the lab or somewhere, or maybe, go shopping on, I don't know, Fry's or somewhere else. Okay. You cannot buy things in moles, right? Usually you buy things in grams. Okay. This is true with, the chemical companies as well, like Sigma Aldrich or, Millipo, somewhere like that. Okay. You need to buy things in grams. But the good thing is you can convert grams to moles to use with our balanced chemical reactions. Okay. So here's an example. Let's say that you bought 6.4 grams of, not octane. I'm sorry, methane. I meant to say methane. CH4 is methane. So for this particular question, we need to use this equation, which we have used in a previous life. Number of moles is equal to mass divided by the molar mass. Here, the lowercase m is the mass. Okay. And the uppercase m is the molar mass. And then lowercase n is the number of moles. Okay. I'm pretty sure that we have seen this before. Okay. In unit 1, module 2. All right. Anyway, now we just plug and chug. So we know the mass, which is 6.4 grams. Always write the units. Otherwise, you're going to make a mistake with the units unnecessarily. 6.4 grams. And divide that by the molar mass of CH4. Carbon relative atomic mass is 12. Hydrogen is 1. You have 4 of them. So 12 plus 4 is 16. I'm sorry, this should be 16. Should be 16. Okay. So CH4 molar mass is 16 grams per mole. So you write 16 grams per mole in the denominator. Okay. Now you see that the grams cancel out. Grams cancel out. You're going to end up with moles. I think that's going to be 0.4. 0.4 moles. All right. Do we have any questions, concerns, comments about this? Anything? All right. Now, the idea is this. If you are given the mass, you cannot use mass directly with the balanced chemical equation. You need to convert that to moles. Okay. That's the whole point here. And how do we do it? You use this equation, right? Make sure that you have this clearly written somewhere. If you forgot about that. Okay. Anyway, with that, let's do this. Okay. So we have same reaction, right? CH4 burned in oxygen or reacting with oxygen to produce CO2 and H2O. Okay. And this should be 2 here and 2 here in the balanced chemical reaction. Okay. Now, first things first. First, I want to know what is limiting my reaction. Okay. To do that, okay, I take the two reactants, CH4 and oxygen. To react with one CH4, I need 2. But right now we have, is it 30 and 20? 30 of CH4 and 20 of oxygen. Is that right? Other way around. Okay. We have 20 of CH4 and 30 of oxygen. Okay, oxygen seems to be limiting now, okay, from, obviously. Anyway, how do we know that? We know oxygen must be limiting because we have more of oxygen, right? No, here's how we do it. With 1 mole of CH4, to react with 1 mole of CH4, we need 2 moles of oxygen. Therefore, to react with 20 moles of CH4, we need how many? To react with 1, we need 2. To react with 20, we need 40. Okay, we need 40. But how many do we have? Only 30. Okay, we have less than what we need, meaning oxygen is calling the shots. Oxygen is the limiting reactant. Okay, so once we identify the limiting reactant, that calls the shots. Okay, now the question is asking the relationship between that and carbon dioxide, right? So they're asking how many carbon dioxide we are getting. So let's see the relationship between oxygen and carbon dioxide. Okay, so oxygen and carbon dioxide. Okay, based on the balanced chemical reaction, if we had 2 moles of oxygen, we are going to get 1 mole of carbon dioxide. With 2, we are going to get 1. With 1, we are going to get 1/2. Okay, with 30, we are going to get 1/2 multiplied by 30, which is 15 moles of carbon dioxide. Okay, that's what we are getting. But we are asking for the mass of carbon dioxide. So we need to convert mass to moles. Moles to mass. So we know number of moles is mass divided by the molar mass, meaning mass is number of moles multiplied by the molar mass. Therefore, 15 moles multiplied by the molar mass of carbon dioxide is, carbon is 12, oxygen is 16, you have 2 of them, 32 plus 12 is 44, 44 grams per mole will give you the mass of carbon dioxide, which is 660. What did you get? 660, 660 grams of carbon dioxide. Okay. Yeah, that's it. That's how we do it. Any questions, concerns, comments about this? Any questions, concerns, comments, anything? Okay. There'll be about 2, maximum 3 questions like this on your exam 4, which is 1 week from Black Friday. Which is 1 week from this Friday. Okay. It's coming up. Okay. All right. Anyway, let's do maybe 1 more. Okay. Most of you got that. That's good. Actually, you know what? Don't open that yet. Let's do this. All right. So to wrap up, unit 4, module 2, I want you to try this. Okay. Let's burn C2H6 in oxygen. Okay. C2H6 reacting with oxygen to produce CO2 and H2O. It's a different reaction now. Not balanced. So we need to balance the chemical reaction. We have 2 carbon atoms on the reactant side. How many do we have on the product side? Everybody. Only 1. So what do? We multiply number of carbon dioxide by 2. Okay. We have 6 hydrogen atoms on the reactant side. How many do we have on the product side? 2. So we multiply number of H2O by 3. So we have 6 there as well. Okay. Now oxygens. We have 2 on the reactant side, but on the product side, we have 2 times 2, 4 from carbon dioxide and 3 from H2O. So together 7. So I'm going to multiply this by 7. Wait a minute. That will give me 14. Okay. Let's divide that by 2 to get 7 oxygen atoms on the reactant side as well. Now, I don't like fractions. To get rid of fractions, I'm going to multiply everything by the denominator. So this will be 2. Here 2 will be cancelled down. And this will be 4. And this will be what? 6. So that should be my balanced chemical reaction. All right. So with that, I want you to tell me the minimum mass of C2H6 required to produce 216 grams of H2O. Okay. Now I'm going to actually set you up like this, guide you a little bit before I, throw you into the water. Okay. Here's what we need to do. Okay. So we have C2H6, oxygen, and CO2 and H2O. The balanced chemical reaction is, what is that? Okay. 2, 7, 4, and 6. We just balanced it. Okay. Now, whenever you are given a question like this, start with what is given. What is given is the mass of H2O. So you are given the mass of H2O, which is 216 grams. Okay. So, but they are asking the mass of C2H6 that is needed, mass of C2H6 needed to produce 216 grams of water. Now, here's the thing. We cannot convert between masses directly. There are three steps involved in between. Okay. First, you need to convert mass to moles of H2O. How do we do this? Number of moles is equal to mass divided by the molar mass. With that, that's step number 1. Okay. Step number 2, from the balanced chemical equation, determine the relationship between the moles of H2O, moles of what is given, and moles of what they are asking. Okay. So that is going to be, then you're going to determine the number of moles of C2H6 that is needed. That is number 2. Okay, that is number 2. And where did it come from? From the balanced reaction. From. Okay, the relationship is coming from the balanced reaction. And then you convert number of moles to the mass using the same equation. Okay, but I'm going to rearrange that a little bit to say mass is equal to number of moles times the molar mass. Okay, that's my third step. All right, those are the 3 steps involved. All right, go ahead. I mean, you can follow these 3 steps individually and end up with the answer. Or, I mean, you can do what we call the dimension analysis or something like that, end up with the same answer as well. I'll show you both ways, okay? I mean, this way is, it's already shown anyway, but I'll show you the other way, okay? So, you are starting with, so you always start with what is given to you. What is given is the mass of water, okay? So, you're going to write that first. You are given 216 grams of H2O. Okay, but you don't want that. You want the grams of C2H6. That's what you want. So see how I'm going to get there now, okay? So I'm going to do this. Now, I want to get rid of the grams of H2O. To do that, I'm going to divide this by the molar mass of H2O. So here I'm going to write 18 grams of H2O because that's how many grams of H2O we have in 1 mole of H2O. Okay. And this is my first step. Step 1, this one. I just divided the mass by the molar mass. Step 1. And why did I do this? I can get rid of the grams of H2O. I can cancel out the grams of H2O. Now I'm going to end up with moles of H2O. Okay. I don't want that either. I want to, get rid of moles of H2O and get to the C2H6 space, right? So to do that, I'm going to go to my balanced chemical reaction and I'm going to look at the molar ratio relationship between the moles of H2O, which is what is given, and C2H6, which is what they're asking for. Okay. I see that it has 6:2. So I'm going to write 6 moles of H2O from the balanced chemical reaction over here. Why? So that I can cancel that out with H2O moles in the numerator here. And then in the numerator, I write 2 moles of C2H6. 2 mole of C2H6. If I do that, I'm going to now end up with moles of C2H6. Guess what? This is my step 2. Okay, this is my step 2. Okay, now what I'm going to do is, I don't want moles, I need the mass, all right? To do that, I'm going to cancel out the moles of C2H6 because with the molar mass of C2H6, right? Because 1 mole of C2H6 has a mass of, let's find the mass, okay? Carbon is 12, you have two of them, 2 times 12, plus hydrogen is 6, hydrogen is 1, you have 6 of them, you have 6 times 1, 2 times 12 is 24, 24 plus 6 is 30, right? So in other words, 1 mole of C2H6 is 30 grams of C2H6. If I do that, guess what? I'm canceling out moles of C2H6 and end up with grams of C2H6. Voila. This is what I need. Okay. Now I take my calculator out and plug and chug these numbers. What are the numbers again? I have in the numerator, I have 216. I have 1. I have 2. I have 30. Okay. And in the denominator, I have 18. I have 6 and I have 1. I don't have right 1. Okay. So if I do this, I'm going to get grams of C2H6. Okay. What did you get? Anybody? Yeah, you got 120. Is that right? 120 grams of C2H6. That's it. That's how we do it.